In 1981, astronomers spotted something they couldn't explain. While charting the cosmos, they discovered a colossal region of nearly nothing. No brilliant galaxies, no star-packed clusters, just emptiness. But this wasn't typical empty space. This was different, unnatural. The zone stretched 330 million light-years wide, so immense you could line up 2,500 Milky Way galaxies end to end just to span it. And yet, it held almost nothing. Where thousands of galaxies should thrive, they found barely 60. They called it the Boötes Void. Here's what haunts scientists to this day. Cosmic voids this colossal shouldn't exist. Not according to everything we understand about gravity, dark matter, and how the universe formed after the Big Bang. Something hollowed out this cavity in the fabric of reality itself. Was it a natural force we haven't discovered, or something far stranger? If you floated at its heart, you'd witness the most isolated view imaginable. The night sky wouldn't shimmer with faraway stars, just endless blackness. The closest galaxy might be so distant that its light started journeying toward you before dinosaurs roamed the Earth. Today, we're venturing inside the largest void in the universe to reveal what forces could forge such breathtaking emptiness, and what it tells us about existence itself. When you look up at the night sky on a clear evening, what do you see? If you're in a city, you might catch a few dozen stars piercing through the light pollution. From a dark, rural location, thousands of stars reveal themselves, along with that pale band of light we call the Milky Way stretching across the heavens like a river of stars. This view has shaped human imagination for millennia. We picture the universe as a vast expanse filled with stars, galaxies spinning through space, glowing nebulae where new suns are born. It's a vision of abundance, of cosmic fertility, of a universe teeming with matter and light. But this picture, as beautiful as it is fundamentally incomplete. It's like looking at a photograph of the ocean's surface and assuming you understand everything beneath. Because for every bright galaxy cluster you can see, for every stellar nursery glowing with the birth of new stars, there are vast regions of space that contain almost nothing at all. These aren't just small gaps between galaxies. They're enormous cosmic deserts so vast that our entire galaxy would be nothing more than a grain of sand in an endless empty beach. And these voids, as they're called, make up the majority of the universe's volume. Think about that for a moment. The universe isn't primarily made of the stuff we can see. Most of it is absence, silence, emptiness on a scale that makes even the largest galaxy seem insignificant. But scientists didn't always know this. For decades, astronomers believed the universe was more or less uniformly filled with galaxies, sprinkled throughout space like stars in the night sky. Sure, some regions were denser than others, but the overall picture was one of relative evenness. The cosmos was thought to be a bit like a well-stirred cosmic soup, with matter distributed fairly evenly throughout. That comfortable assumption was about to be shattered, and the discovery that would change everything came from an unexpected direction, from a team of astronomers who were simply trying to map how galaxies are distributed across space. They had no idea they were about to discover something that would make them question the very fabric of reality itself. But before we reveal what they found, you need to understand just how shocking their discovery was. And to do that, we need to talk about something that sounds simple, but is actually one of the most powerful tools in astronomy: light. Have you ever stood by a railroad track as a train rushes past, horn blaring? You've probably noticed something strange. As the train approaches, the horn sounds higher in pitch. Then, the moment it passes you, the pitch suddenly drops lower. The horn itself hasn't changed, but the sound waves reaching your ears have been compressed or stretched by the train's motion. This is the Doppler effect, and it's one of those everyday phenomena that holds the key to unlocking the deepest mysteries of the universe. Because the same thing happens with light. When a galaxy moves away from us, the light waves it emits get stretched out during their journey across space. Longer wavelengths mean redder light, which is why astronomers call this phenomenon redshift. The faster a galaxy recedes, the more its light shifts toward the red end of the spectrum. And here's the crucial part. Thanks to the expansion of the universe, the farther away a galaxy is, the faster it's moving away from us. This gives astronomers something remarkable, a cosmic measuring tape. By precisely measuring how much a galaxy's light has been redshifted, they can calculate its distance from Earth with stunning accuracy. It's like being able to tell exactly how far away a distant city is just by listening to the pitch of a train whistle. In the late 1970s and early 1980s, a team led by astronomer Robert Kirshner decided to use this cosmic measuring tape to create something unprecedented, a three-dimensional map of the universe. Not just a flat picture showing where galaxies appear in the sky, but a true volumetric chart revealing their actual positions in space. Their method was painstaking. Night after night, they pointed their telescopes at galaxies in a specific region of the sky, collecting the faint light that had travelled for hundreds of millions of years to reach Earth. For each galaxy, they used a spectrograph to split its light into a rainbow of colours, searching for the telltale fingerprints of hydrogen and other elements. By measuring how much these fingerprints had shifted toward the red, they could calculate each galaxy's distance. The region they chose to study was in the direction of a constellation called Boötes, named after a celestial herdsman from Greek mythology. It seemed like an ordinary patch of sky, no different from thousands of others. There was no reason to expect anything unusual. But as their data accumulated, something bizarre began to emerge. In one particular slice of their three-dimensional map, at distances ranging from about 500 million to 750 million light-years away, they found far fewer galaxies than expected. Not just a little fewer, dramatically, shockingly fewer. At first, they thought it might be a mistake. Perhaps their telescopes weren't sensitive enough to detect the fainter galaxies in that region. Maybe there was obscuring dust blocking their view. They checked their instruments, verified their calculations, and looked for any possible source of error. But the more they checked, the more certain they became. This wasn't an instrumental artifact or an observational bias. The void was real. They were staring at a genuine hole in the universe, a region of space where galaxies simply didn't exist in the numbers they should. When they finally published their findings in 1987, the astronomical community was stunned. The Boötes Void, as they named it, was estimated to be roughly 250 million light-years in diameter. To put that in perspective, our entire Milky Way galaxy, with its hundreds of billions of stars, is only 100,000 light-years across. You could line up 2,500 Milky Way galaxies end to end just to span the width of this cosmic hole. But the true shock wasn't just its size, it was what the void represented. The universe, they realised, wasn't a smooth distribution of galaxies. It was structured, organised into an intricate pattern of filaments and walls, with enormous empty bubbles scattered throughout. The Boötes Void was one of these bubbles, and its existence meant that the cosmos was far stranger and more complex than anyone had imagined. Yet even as scientists celebrated this groundbreaking discovery, a darker question began to emerge. Because voids like this one don't form randomly. Something had to have created them. Something had shaped the universe into this bizarre sponge-like structure, with matter concentrated in some regions and almost completely absent in others. The answer to that question would lead astronomers down a path into one of the most mysterious aspects of reality itself. But before we get there, you need to understand just how empty the Boötes Void really is. And I mean truly, incomprehensibly empty. Let's play with some numbers for a moment, because sometimes the only way to grasp the incomprehensible is through sheer arithmetic. The Boötes Void spans approximately 330 million light-years in diameter. That's 330 million years of travel at the speed of light, the fastest speed possible in our universe. Light moves at 186,000 miles per second, or about 671 million miles per hour. At that incomprehensible velocity, it would still take 330 million years to cross from one side of the void to the other. To put this in perspective, when light from the far edge of the Boötes Void first began its journey toward us, life on Earth was just beginning to crawl out of the oceans. No trees existed, no animals walked on land. The continents were arranged in completely different configurations. That's how long light takes to traverse this cosmic emptiness. But it gets more mind-bending. The Boötes Void isn't just a flat circle, it's a three-dimensional sphere of emptiness. Its volume is almost incomprehensible. You could fit billions upon billions of galaxies the size of the Milky Way inside its boundaries, and yet astronomers have identified only about 60 galaxies within its entire volume. 60 out of thousands that should be there. Imagine you're standing in the centre of the void, on a planet orbiting a star in one of these lonely galaxies. You look up at your night sky and see the familiar stars of your own galaxy above you. But beyond that, nothing. The nearest neighbouring galaxy might be 50 million light-years away, appearing as little more than a faint smudge even through the most powerful telescope. The Andromeda Galaxy, visible to the naked eye from Earth, would be completely invisible to you, trillions of times too distant to detect. The cosmic web, that vast interconnected network of galaxy filaments and clusters that makes up the universe's large-scale structure, would be utterly invisible from your vantage point. You would have no idea that the universe is teeming with galaxies, no clue that trillions of stars exist beyond your lonely island. Your civilization might look at the sky and conclude that your galaxy is the entire universe, floating alone in an infinite void. This isolation isn't just philosophical, it's physical. The density of matter in the Boötes Void is estimated to be less than 10% of the universe's average density. In some regions, it might be even lower, perhaps just 1% or 2% of what's typical elsewhere. That's not just sparse, that's approaching true emptiness. To understand what this means, consider that the average density of the universe is already incredibly low, roughly 1 hydrogen atom per cubic metre. That's far emptier than any vacuum we can create in a laboratory on Earth. But in the Boötes Void, you might find only 1 atom per 10 cubic metres, or even less. It's emptiness taken to an almost absurd extreme. Yet here's what makes this even stranger. The void isn't perfectly empty. Those 60 lonely galaxies scattered throughout its volume prove that. These galaxies, often called void galaxies or lonely galaxies, are among the most isolated objects in the universe. Some of them are separated from their nearest neighbours by tens of millions of light-years, distances that make intergalactic space in our region look positively crowded by comparison. These lonely galaxies are scientific gold mines. Because they're so isolated, they haven't been shaped by the gravitational interactions that influence most galaxies. They don't merge with neighbours, don't get their gas stripped away by ram pressure as they move through dense clusters, don't experience the tidal forces that distort galactic structure. They're pristine, evolving at their own pace, governed only by their internal dynamics. Studying them tells us what galaxies look like when they grow up in peace, without the chaos of a crowded cosmic neighbourhood. And what scientists have found is fascinating. These void galaxies tend to be bluer, indicating more active star formation. They retain their gas more efficiently. They're often spiral or irregular in shape, rather than the elliptical galaxies common in dense clusters. But these rare islands of matter only emphasise the overwhelming emptiness around them. The Boötes Void isn't defined by what's in it. It's defined by what's missing, and that brings us back to the central mystery. What happened here? Why is this region so profoundly empty? The answer, scientists have discovered, lies in something that happened not in the Boötes Void itself, but in the very first moments after the Big Bang. To understand the void, we have to rewind time itself, back to when the universe was less than a second old. But before we take that journey backward through cosmic time, there's something else you need to know about the Boötes Void. Something that might be even more unsettling than its size or emptiness. Because the Boötes Void isn't alone, it's not, even unusual. And that realization would fundamentally change how we see the universe. For millennia, humans have looked at the night sky and seen patterns, constellations, planets tracing paths across the zodiac, the Milky Way arcing overhead. We've always sought order in the cosmos, ways to map and understand the arrangement of celestial objects. But until the late 20th century, we had no idea just how profoundly structured the universe really is. The discovery of the Boötes Void was just the beginning. It was like finding a single piece of a vast cosmic puzzle, and once astronomers knew what to look for, they began finding more pieces everywhere they turned. Throughout the 1980s and 1990s, massive galaxy redshift surveys like the Sloan Digital Sky Survey began mapping millions of galaxies across vast swaths of the sky. When astronomers plotted these galaxies in three-dimensional space, something extraordinary emerged. The universe wasn't a random scattering of galaxies. It had structure, astonishing, beautiful, almost architectural structure, galaxies arranged, themselves into long, thin filaments, like threads in a cosmic tapestry. These filaments stretched for hundreds of millions of light years, connecting dense knots of galaxy clusters at their intersections. And between these filaments, taking up the vast majority of space, were voids, huge bubbles of emptiness, like the holes in Swiss cheese or the spaces in a sponge. This structure is now known as the cosmic web, and it's one of the most important discoveries in the history of astronomy. The Boötes Void isn't an anomaly, it's a fundamental component of this web. It's one of the larger bubbles in the cosmic foam, a defining feature of the universe's architecture rather than a strange exception. Imagine you're looking at a massive three-dimensional map of the universe. The galaxy clusters appear as bright knots of light. The filaments connecting them glow like luminous threads, and the voids appear as dark bubbles, vast regions where the lights simply fade away. It looks uncannily like the structure of a brain with neurons connected by axons and dendrites, or like a biological cell with its complex internal scaffolding. This resemblance isn't coincidental. The universe, biological systems, and many other complex structures in nature all follow similar patterns because they're shaped by similar principles: the flow of energy, the accumulation of resources, the optimization of connections. The cosmic web is the universe organizing itself in the most efficient way possible given the laws of physics. But why this structure? Why filaments and voids rather than a smooth, even distribution? The answer takes us back to the beginning, to the moment of creation itself. In the first fraction of a second after the Big Bang, the universe was incredibly hot, dense and remarkably uniform, but not perfectly uniform. Quantum fluctuations, tiny random variations in the density of matter and energy, created microscopic ripples in the fabric of space-time. These ripples were almost incomprehensibly small, just 1 part in 100,000 variations in density. But that was enough, because the universe has a sculptor, an invisible artist that takes these tiny imperfections and amplifies them over billions of years into the grand structures we see today. That sculptor is gravity, and its assistant providing most of the raw material is dark matter. Here's where things get really interesting. The visible matter we see, the stuff that makes up stars and planets and you and me, is only about 5% of the universe's total mass and energy. Another 27% is dark matter, an invisible substance that doesn't interact with light but exerts tremendous gravitational force. The remaining 68% is dark energy, an even more mysterious force that acts as a kind of anti-gravity, pushing space apart. When the universe was young, the tiny overdense regions contained slightly more dark matter than average. That extra dark matter had slightly more gravitational pull, which drew in even more dark matter and ordinary matter from the surrounding regions. It's a snowball effect. More matter means more gravity, which attracts even more matter, which increases gravity further. Over hundreds of millions of years, these slightly overdense regions collapsed under their own gravity, forming the first galaxies and galaxy clusters. The matter streamed along gravitational highways, natural channels where the pull of gravity was strongest. These highways became the filaments of the cosmic web. But what about the underdense regions? The places where there was slightly less dark matter to begin with? In these regions, gravity had less to work with. As matter was pulled toward the overdense areas, it was simultaneously pulled away from the underdense ones. These regions were evacuated, drained of their contents like water flowing out of a bathtub. And as the universe expanded, stretching space itself, these already empty regions grew even larger and emptier. These evacuated regions became the cosmic voids. The Boötes Void is one of them, a place where the initial conditions left slightly less dark matter, which meant less gravity to hold on to the matter that was there. Over billions of years, that matter flowed away toward the denser regions, leaving behind a vast bubble of near emptiness. But there's another force at work here, something that makes voids even more profound and mysterious. Remember dark energy? That's 68% of the universe that acts as anti-gravity. In regions where matter is dense, where galaxy clusters hold billions of galaxies together with their immense gravitational pull, dark energy's expansive push is overwhelmed. Gravity wins. But in voids, where matter is scarce and gravity is weak, dark energy dominates. It pushes the sparse matter apart even faster than the universe's normal expansion would. Voids aren't just empty, they're actively expanding, growing larger and emptier with every passing moment. This means the Boötes Void isn't static. It's not a hole that was carved out and now sits frozen in space. It's a growing bubble, continuously expanding, becoming more profoundly empty as cosmic time marches forward. The lonely galaxies within it are being pushed farther and farther apart, isolated islands drifting in an ever-expanding ocean of nothingness. And here's the unsettling part. This process is accelerating. The expansion of the universe has been speeding up for the last several billion years, driven by dark energy. As time goes on, voids will grow even faster. The cosmic web will stretch and thin. Eventually, in the unimaginably distant future, the universe might become so spread out that every galaxy is isolated in its own void, unable to see any others, alone in an infinite darkness. But we're getting ahead of ourselves, because while we now understand how voids form, there's still something deeply mysterious about the Boötes Void specifically. It's one of the largest voids ever discovered. Its emptiness is extreme even compared to other voids. And some scientists have wondered, is there something more going on here? Something beyond the normal process of structure formation? That question brings us to some of the more speculative ideas about what the Boötes Void might represent. Ideas that push the boundaries of our understanding of physics, space, and time itself. In science, whenever you find something that seems unusual, even by the standards of unusual things, you have to ask, is this truly an outlier? Or are we missing something fundamental about how the universe works? The Boötes Void is certainly unusual. While many voids exist throughout the cosmos, few are as large or as empty as this one. This has led some researchers to wonder whether its formation involves something beyond the standard processes we've discussed. Could there be exotic physics at play? Could the void tell us something new about dark matter or dark energy? One intriguing possibility involves the nature of dark matter itself. We know dark matter exists because of its gravitational effects, but we don't actually know what it is. Physicists have proposed numerous candidates: WIMPs, weakly interacting massive particles, axions, sterile neutrinos, even primordial black holes left over from the first moments after the Big Bang. Different types of dark matter behave differently. Some forms would clump together readily, forming dense halos around galaxies. Others would remain more diffuse, spreading out over larger volumes. If the region that became the Boötes Void had a different type or lower initial concentration of dark matter than average, it might explain why it grew into such an exceptional void. But there's no strong evidence for this idea. The Boötes Void seems to fit well within our standard models of structure formation, even if it represents an extreme example. Sometimes nature just produces outliers through random chance, regions where conditions happen to be particularly favourable for void formation. Another speculation involves dark energy. Most models treat dark energy as a constant, uniform force pervading all space equally. But what if dark energy isn't uniform? What if its strength varies from place to place, or changes over time? In regions where dark energy was stronger, voids might grow larger and emptier. The Boötes Void could potentially be a region where dark energy is slightly stronger than average, causing more extreme expansion. Again, there's no conclusive evidence for this, but the Boötes Void is an excellent laboratory for testing such ideas. By measuring precisely how fast it's expanding, how its shape evolves over time, and how the galaxies within it move, scientists can constrain the properties of dark energy. Any deviations from the expected behaviour might hint at new physics. There's also the question of whether the void contains anything truly unexpected. Most of the matter in the universe emits or absorbs light in some way, making it detectable. But what if there are forms of matter we simply can't see with any current technology? What if the void isn't as empty as it appears, but contains exotic material that doesn't interact with light at all? This seems unlikely. We can detect dark matter through gravitational lensing, the bending of light from background objects. If the void contained large amounts of invisible matter, we'd see its gravitational effects. The fact that it acts like a genuine underdensity suggests it really is as empty as it seems. But perhaps the most profound mystery isn't about exotic physics at all. It's about what the existence of such voids tells us about the universe's fundamental nature. The fact that most of space is empty, that matter is concentrated into a delicate web surrounding vast bubbles of nothingness. This suggests something important about how the cosmos operates. The universe, it seems, likes to organize itself into hierarchies. Atoms form molecules, molecules form cells, cells form organisms, organisms form ecosystems. At the cosmic scale, matter forms stars, stars form galaxies, galaxies form clusters, and clusters form superclusters connected by filaments. Each level of organization emerges from the interactions of the level below it. But the voids represent the space between these hierarchies. They're the negative space, the canvas on which the cosmic artwork is painted. Without them, the universe would be a chaotic mess, matter distributed evenly throughout space with no structure at all. The voids define the web, just as the silence between notes defines music. This raises a philosophical question. Is emptiness just an absence, or is it something in its own right? The physicist Wheeler once asked, is empty space really empty, or is it filled with virtual particles and quantum fluctuations? The Boötes Void might look empty, but at the quantum level it's seething with activity, particles and antiparticles constantly appearing and annihilating, energy fluctuating in and out of existence. Even in the deepest void, space itself is never truly nothing. It's a stage on which the quantum dance plays out, a field of possibilities that could, under the right conditions, give rise to new structure and complexity. But here's what really keeps cosmologists up at night. The voids are growing. As the universe expands and dark energy pushes space apart, the Boötes Void and its siblings will continue to swell, becoming larger and emptier with each passing billion years. Eventually, the filaments of the cosmic web will thin and break. Galaxy clusters will become isolated islands separated by unimaginable distances. In the far future, perhaps 100 billion years from now, any civilization living in a galaxy within a void will have no evidence that other galaxies exist. The expansion of space will have carried everything else beyond their cosmic horizon, making it forever invisible. They'll look up at their night sky and see only their own stars, with no hint of the vast cosmic web that once surrounded them. This future isolation is sometimes called the Big Empty, and it's one possible fate of our universe. Not a dramatic ending like the Big Crunch, where everything collapses back together, but a slow, cold fade out as structures drift apart and the universe becomes an impossibly vast, dark, empty place. Yet even this bleak future holds a strange beauty, because the story of the universe is, in a sense, the story of structure emerging from simplicity and then dissolving back into it. The Big Bang began with perfect uniformity. Tiny fluctuations grew into the cosmic web, and eventually expansion will erase that web, returning the universe to a state of near uniformity again, not by compression, but by infinite expansion. The Boötes Void is a glimpse of that future. It shows us what the universe is becoming, a place where emptiness dominates, where isolation is the norm, where the cosmic connections that bind galaxies together slowly dissolve into the growing dark. But we're not there yet. For now, we live in a universe still rich with structure, still full of cosmic wonders. The void exists, yes, but so do we, alive on a planet orbiting a star in a galaxy that's part of a vast interconnected web spanning the observable universe, and that brings us to perhaps the most humbling aspect of the Boötes Void, what it tells us about our place in the cosmos. Because understanding the void means understanding where we are, and how lucky we are to be here at all. Think about addresses for a moment. Your home has a street address, a city, a state, a country. Each level of this address tells you something about where you are in relation to the larger world. But have you ever thought about your cosmic address? Where Earth sits in the vast architecture of the universe? Let's build it up layer by layer. Start with Earth, the third planet from the Sun in our solar system. Our Sun is one of roughly 200 to 400 billion stars in the Milky Way galaxy, a barred spiral galaxy about 100,000 light-years across. We're located in a minor spiral arm called the Orion Spur, about 27,000 light-years from the galactic centre. But the Milky Way doesn't exist alone. It's part of a small collection of galaxies called the Local Group, which includes our galaxy, the Andromeda Galaxy, the Triangulum Galaxy, and about 50 smaller dwarf galaxies. The Local Group spans roughly 10 million light-years. The Local Group in turn is being gravitationally pulled toward the Virgo cluster, a massive collection of thousands of galaxies about 55 million light-years away. Both our Local Group and the Virgo cluster are part of an even larger structure called the Laniakea supercluster, which contains about 100,000 galaxies and spans 500 million light-years. So your cosmic address is Earth, Solar System, Milky Way Galaxy, Local Group, Virgo Supercluster, Laniakea Supercluster. Now here's the important part. All of these structures, from our galaxy to our supercluster, are part of the cosmic web. We live in one of the dense regions, along a filament of galaxies where matter has accumulated over billions of years. We're in a cosmic city, a bustling neighbourhood where galaxies are relatively close together and gravitational interactions are common. The Boötes Void lies far beyond our local structures, hundreds of millions of light-years away in a completely different part of the cosmic web. It's in a region where the filaments are thin or absent, where the web has its largest gaps. This means we're fortunate in a way we rarely think about. If our galaxy had formed inside a cosmic void, our view of the universe would be radically limited. We might never have discovered that other galaxies exist. We certainly wouldn't see the cosmic web with anything like the clarity we do. Our entire understanding of cosmology would be delayed by centuries or millennia. But because we live in a dense region, surrounded by thousands of nearby galaxies, and with clear views of distant superclusters, we've been able to map the universe's structure and understand its history. We're like astronomers who happen to set up our observatory in the perfect location, with an unobstructed view of the cosmos in all its complexity. Yet this realization also brings a sobering perspective. The cosmic web is temporary. The structures we see around us, the filaments and superclusters, won't last forever. In the deep future, as the universe continues its accelerated expansion, even our dense regions will thin out. The Virgo cluster will drift away from us. The Local Group will remain gravitationally bound, but everything beyond it will recede beyond visibility. Eventually, Earth's distant descendants, if any exist, will look up at a night sky that contains only the handful of galaxies in our Local Group. The rest of the universe will have expanded away beyond detection. They'll live in their own void, created not by initial underdensity, but by the relentless expansion of space. This future isolation makes the present moment precious. Right now, in this cosmic era, we can see farther and learn more about the universe than any civilization will be able to in the far future. We're living in what might be called the golden age of cosmology, when the universe is old enough to have developed complex structures, but young enough that those structures are still visible. The Boötes Void, then, isn't just a curiosity, it's a preview of the universe's future. It shows us what happens when expansion wins over gravity, when isolation dominates over connection, when the cosmic web unravels into scattered fragments. But there's another angle to consider. What if, somewhere in one of those lonely galaxies in the Boötes Void, an intelligent civilization exists? What would their cosmology look like? How would they understand their place in the universe? This isn't just an abstract question. It gets at something fundamental about how observation shapes understanding. Let's explore this thought experiment in depth, because it reveals something profound about the relationship between location, perception, and knowledge. Close your eyes and imagine you're not on Earth. You're standing on a planet orbiting a star in a galaxy deep within the Boötes Void, one of those 60 lonely galaxies scattered across 330 million light-years of near emptiness. You look up at your night sky. Above you, the stars of your home galaxy create familiar constellations, patterns your civilization has known for millennia. But beyond your galaxy, almost nothing. Your most powerful telescopes can detect perhaps a dozen faint smudges of light, other void galaxies tens or hundreds of millions of light-years away. No galactic clusters, no filaments, no cosmic web. For thousands of years, your civilization believed your galaxy was the entire universe. Why wouldn't you? There was no evidence to suggest otherwise. When your scientists first developed telescopes and began mapping the heavens, they catalogued the stars and nebulae within your galaxy, but found no hint of anything beyond. Eventually, better instruments revealed those. Few distant smudges. Your scientists debated, were these mysterious objects within your galaxy, or could they be separate island universes impossibly far away? The debate raged for generations, because the distances involved were so vast that measuring them was extraordinarily difficult. Finally, after centuries of work, your astronomers managed to measure the redshifts of these distant objects. They were galaxies, separate from your own, at distances of tens of millions of light-years. This was a revolution in thought comparable to Copernicus revealing that Earth wasn't the centre of the solar system. But here's where your cosmology diverges radically from ours. On Earth, once we discovered other galaxies, we quickly found millions of them. Our universe revealed itself as teeming with galaxies, arranged in a vast cosmic web. Your universe, in contrast, appears nearly empty. You found a few dozen other galaxies, all separated by unimaginable distances. Your scientists develop a cosmology based on isolation. They calculate that the universe must have started with the Big Bang, yes. The cosmic microwave background radiation, that faint afterglow from the early universe, is still detectable even in the void. Redshift measurements confirm that the universe is expanding, but the structure they observe is radically different from what we see. Where we see filaments and clusters, you see scattered islands in an infinite ocean. Your models of structure formation have to explain why galaxies are so spread out, why there are vast distances between them. Here's the fascinating part. Your scientists might actually have an easier time detecting dark energy. On Earth, discovering the accelerated expansion required observing distant supernovae and carefully measuring their redshifts and distances. But in a void, where local gravitational influences are minimal, the effects of dark energy are more pronounced. Your galaxy, and the few others around you, are all accelerating away from each other at rates that clearly exceed what ordinary expansion would predict. You might discover dark energy earlier in your scientific development than we did, leading to a cosmology centered on repulsion rather than attraction. Where we focused on how gravity builds structures, you focus on how dark energy tears them apart. Your civilization's philosophy would be shaped by this profound isolation. On Earth, religions and philosophies have grappled with our place in a vast cosmos full of stars and galaxies. Your philosophers grapple with loneliness on a cosmic scale. Are you alone in the universe? Your evidence suggests yes. In all the observable universe, you see only a handful of galaxies. The chances of any of them harboring intelligent life seem vanishingly small. This could lead to a deep sense of cosmic responsibility. If you are alone, or nearly alone, then your survival matters immensely. There's no one else out there to carry the torch of consciousness. Your civilization might develop a profound ethic of preservation, an understanding that you must survive because you might be all there is. Alternatively, it might breed a kind of cosmic existentialism. What does anything matter in an almost empty universe? If you're isolated in a void with no possibility of contact with other civilizations, no hope of seeing other galaxies as anything more than distant points of light, does your existence have meaning? But perhaps your isolation would drive innovation. Unable to study other galaxies in detail, you might turn inward, developing incredibly sophisticated physics and mathematics to understand the fundamental nature of reality. You might push technology to its limits, trying to bridge the impossible distances to your nearest neighbours. Or maybe you'd accept the isolation and build a civilization focused entirely on your own galaxy. You'd have no fear of external threats, no worry about colliding with another galaxy. Billions of years hence, your resources, while limited to one galaxy, would still be vast by any practical measure. You could build a stable, sustainable society that lasts for trillions of years. There's a haunting beauty to this thought experiment, because it reveals how contingent our knowledge is on our circumstances. We're lucky to live in a dense region where the universe's complexity is on full display. But that luck is temporary. Given enough time, every civilization might end up in a void, as cosmic expansion erases the web and isolates all galaxies. In that far future, civilizations everywhere will face the same lonely sky that void dwellers see now. They'll look up and see only their own stars, with no evidence that the universe was once full of galaxies, no hint of the cosmic web that defined the universe's structure for billions of years. This is sometimes called the Great Fade-Out of cosmology. The evidence for the Big Bang will become harder to detect. The cosmic, microwave background will redshift into invisibility. Distant galaxies will vanish beyond the cosmic horizon. Future scientists will face an impoverished universe with fewer clues about cosmic history than we have today. So the Boötes Void isn't just a current feature of the universe, it's a preview of what awaits everywhere. It's what isolation looks like on a cosmic scale, and it reminds us that our current view of a richly structured, densely populated cosmos is a temporary phase, a golden era that won't last forever. But let's return from this speculative future to the present, because there are still aspects of the void we haven't explored. Specifically, how do scientists actually study something that's defined by the absence of light? What techniques and technologies let us map and measure emptiness? The answer reveals some of the most ingenious observational strategies in modern astronomy. Studying cosmic voids presents a unique challenge in observational astronomy. When you observe a galaxy, you collect its light and analyze its spectrum. When you observe a nebula, you image its glowing gas. But how do you observe nothingness? How do you map a void? The answer lies in indirection. You study a void by studying what surrounds it and what's missing from it. The primary tool, as we've discussed, is the redshift survey. By systematically measuring the distances to millions of galaxies across vast regions of the sky, astronomers build three-dimensional maps showing where galaxies are and, crucially, where they aren't. Voids appear as gaps in this distribution, regions where galaxies are significantly rarer than expected. But there's an art to defining a void's boundaries. Voids don't have sharp edges. Instead, there's a gradual transition from the high-density filaments surrounding a void to its underdense interior. Scientists use statistical methods to identify where this transition occurs, defining a void as a region where the galaxy density falls below some threshold, typically around 20% of the cosmic average. Different surveys use different definitions, which is why estimates of void sizes and numbers vary. But all agree on the basic picture. Voids are real, large, and numerous. Modern redshift surveys have become incredibly powerful. The Sloan Digital Sky Survey, which operated from 2000 to 2020, mapped the positions and distances of millions of galaxies. Its successor, the Dark Energy Spectroscopic Instrument (DESI), is even more ambitious, aiming to measure redshifts for 35 million galaxies and quasars. These surveys use specialized instruments that can measure hundreds or thousands of spectra simultaneously. By placing optical fibers at precise positions on a focal plane, astronomers can observe hundreds of galaxies in a single exposure. This multiplexing dramatically increases efficiency, allowing surveys to map vast volumes of space in reasonable timeframes. For studying voids specifically, scientists look for regions where very few fibers capture galaxy spectra. These empty patches on the sky, when combined with distance information, reveal the three-dimensional structure of voids. But redshift surveys aren't the only tool. Gravitational lensing provides another window into void structure. While voids are underdense, they're not completely empty of mass. The sparse dark matter within them still exerts gravitational effects, subtly bending the light from more distant galaxies. By carefully measuring these distortions across large areas of sky, astronomers can map the distribution of dark matter, including the reduced density within voids. This technique is challenging because void lensing signals are weak, but next-generation surveys like the Vera C. Rubin Observatory's Legacy Survey of Space and Time will have the sensitivity to detect them. Another fascinating technique involves radio astronomy. The universe is filled with neutral hydrogen gas, left over from the early universe and ejected from galaxies by various processes. This hydrogen emits radio waves at a wavelength of 21 centimeters, which radio telescopes can detect. Most of the universe's neutral hydrogen is too diffuse to detect with current technology, but future instruments like the Square Kilometre Array, SKA, will be sensitive enough to map it throughout cosmic voids. This will reveal whether voids contain more gas than expected, or whether they're truly as empty of ordinary matter as they appear. Scientists also study the cosmic microwave background for void signatures. When CMB photons travel through a void, they experience a slight change in energy due to the different gravitational environment. This creates a subtle cold spot in the CMB temperature map, which can be detected through careful analysis. The most famous example is the CMB cold spot, an anomalously cold region in the microwave sky. Some scientists have proposed that it's caused by an enormous supervoid along our line of sight, possibly even larger than the Boötes Void. While this explanation remains controversial, it demonstrates how voids can leave their imprint on the most ancient light in the universe. Supernovae also serve as void probes. When a supernova explodes in or near a void, its light travels through underdense regions, experiencing less absorption and scattering than light traversing denser areas. By comparing supernovae in different environments, astronomers can learn about the matter distribution throughout the universe. Finally, there's theoretical work. Sophisticated computer simulations model how the universe evolved from its early uniform state to the cosmic web we observe today. By varying the parameters, such as the amount of dark matter, the strength of dark energy, and the amplitude of initial fluctuations, scientists can explore which conditions produce voids resembling those we observe. These simulations confirm that voids like the Boötes Void arise naturally from gravitational collapse and cosmic expansion. They're not anomalies requiring exotic physics, but predictable consequences of ordinary structure formation. The simulations even predict how many voids of different sizes should exist, predictions that observations generally confirm. This convergence between theory and observation is one of cosmology's great successes. It shows that our understanding of the universe's large-scale structure, including its voids, rests on solid foundations. Yet mysteries remain. The exact role of dark energy in void expansion, the properties of the sparse gas within voids, the evolution of void galaxies, all of these topics are areas of active research. Each new survey and telescope brings fresh insights, refining our picture of these cosmic empty spaces. And there's a tantalizing possibility. Could voids tell us something new about physics? Some theories predict that dark energy might not be uniform, or that gravity might behave differently on the larger scales. Voids, where matter is sparse and dark energy's effects are pronounced, could be the key to testing these ideas. If we discover that voids expand faster or slower than predicted, it might hint at modifications to general relativity or new properties of dark energy. This would be revolutionary, potentially opening new windows into the fundamental nature of space-time and energy. So while voids might seem like nothing, they're actually somethings, regions of space with unique properties that can teach us about the universe's composition, history, and fate. The Boötes Void, as one of the largest and best-studied examples, sits at the forefront of this research. But there's one more angle we haven't explored. Throughout this journey, we've focused on the void itself. Now let's zoom out and ask, what does the existence of cosmic voids tell us about the ultimate fate of the universe? Where is all of this heading? Time, in cosmology, is measured in billions of years. The universe is currently about 13.8 billion years old. Earth formed about 4.5 billion years ago. Humans have existed for perhaps 300,000 years, and modern civilization for just a few thousand. We're used to thinking of the universe as eternal and unchanging on human timescales, because it essentially is. But on cosmic timescales, everything changes. The universe is not static. It's evolving, driven by the interplay of gravity and expansion, matter and energy. And the direction of that evolution is becoming clear, toward greater emptiness, cooler temperatures, and deeper isolation. The Boötes Void gives us a preview of this future. Right now, it's an outlier, an unusually empty region in a universe that still has plenty of structure. But as cosmic time marches forward, more regions will come to resemble it. Here's why. The universe's expansion is accelerating, driven by dark energy. This acceleration means that anything not gravitationally bound together will be pushed apart at ever-increasing speeds. Galaxy clusters will remain intact, held together by their immense gravity, but the filaments connecting clusters will stretch and thin. Eventually they'll break. In about 100 billion years, galaxies beyond our local group will have receded so far that their light will be redshifted beyond detection. They'll cross our cosmic horizon, moving away faster than light can travel. This doesn't violate relativity. It's space itself expanding, not objects moving through space. From Earth, or wherever our descendants might be, the observable universe will shrink dramatically. The cosmic web will vanish from view. The only galaxies visible will be those in our local group, eventually merging into a single giant elliptical galaxy. Future astronomers, if any exist, will look up at a night sky containing only their own galaxy's stars. No other galaxies. No cosmic microwave background. It will have redshifted to undetectable wavelengths. No evidence of the Big Bang or the universe's expansion. Their cosmology will be impoverished, with far fewer clues about cosmic history than we have today. They'll live in their own void, not because they're in an underdense region, but because expansion has pushed everything else beyond visibility. The universe will still exist, still be full of galaxies, but each will be isolated in its own bubble of observable space. This scenario, sometimes called the Big Empty, is one possible fate of our universe. Not a dramatic ending, but a slow fade out into darkness and isolation. But it gets stranger. As the universe continues expanding, even gravitationally bound structures will eventually be affected. Galaxies will exhaust their gas supplies, with no new material accreted from the intergalactic medium. Star formation will cease. Stars will age and die, with no new ones born to replace them. In about 1 trillion years, all the stars in the universe will have burned out or died. Galaxies will be filled with dead remnants, white dwarfs, neutron stars, black holes. The universe will enter what's called the degenerate era, lit only by occasional flashes when dead stars collide. Eventually, even these remnants will decay. Protons, if they're unstable as some theories suggest, will decay over 10 to the power of 40 years or so. Black holes will evaporate through Hawking radiation, the last supermassive ones disappearing after 10 to the power of 100 years. What's left? According to our best theories, the universe will enter the dark era, an unimaginably vast expanse of time where nothing exists except a thin soup of photons and fundamental particles spread across an exponentially expanding space. The voids won't just grow, they'll win. The entire universe will become a void, with no structures, no complexity, no information. Just darkness, cold, an unimaginable emptiness stretching toward infinity. This might sound depressing. The ultimate fate of everything we know, everything we've built, every spark of consciousness that's ever existed, all destined to dissolve into an expanding void. It's a vision of cosmic heat death, where entropy maximizes and nothing interesting can ever happen again. But there's another way to think about it. The universe is not a story with a happy or sad ending. It's a process, a continuous evolution of structure and complexity. Right now, in our cosmic epoch, conditions are right for stars, planets, life and consciousness. We're living in a golden age of cosmic structure, when the universe is rich with possibilities. The voids, in this light, aren't harbingers of doom. They're part of the natural life cycle of the cosmos. Just as individual stars are born, live and die, so too does the universe cycle through phases of concentration and dispersal. The Big Bang began with perfect uniformity. Structure emerged through gravitational collapse, and eventually expansion will return the universe to a state of uniformity, not through compression but through infinite dilution. The Boötes Void is a snapshot in this process. It shows us the direction we're heading, but it also reminds us that we're not there yet. Right now, the universe is full of stars and galaxies, full of structure and wonder. We're here to witness it, to understand it, to tell its story. And perhaps that's the deepest message of the void. It's a reminder that everything is temporary. Galaxies will die, the cosmic web will disperse, even the universe itself will fade into darkness. But that makes this moment, right now, all the more precious. We're alive in an era when the universe is knowable, when we can look up at the night sky and see the cosmic web in all its glory, when we can probe the deepest mysteries of space and time. The void teaches us that emptiness is fundamental to the cosmos. But so is structure, so is complexity, so is the brief window where consciousness can emerge and contemplate its own existence. In the end, the Boötes Void isn't just a cosmic curiosity. It's a profound statement about the nature of reality, about the impermanence of all things, about the balance between matter and nothingness that defines our universe. We've journeyed through the Boötes Void, from its shocking discovery in 1981 to its implications for the universe's ultimate fate. We've explored how it formed, what it contains, and what it tells us about the cosmic web's intricate structure. This region of space, 330 million light-years across and almost entirely empty, stands as one of the most remarkable features in the observable universe. Where 2,000 galaxies should exist, we find only 60. It's a hole in the cosmos, a bubble in the cosmic foam, a preview of the universe's distant future. But it's also a reminder of our incredible fortune. We live in a dense region of the cosmic web, surrounded by galaxies and clusters, with a clear view of the universe's structure. We exist in an era when the cosmos is still young enough to be interesting, still structured enough to be beautiful. The void is growing. Someday, in the unimaginable future, everywhere will be a void. But that day is trillions of years away. For now, we have stars and galaxies, planets and life, consciousness and wonder. The Boötes Void teaches us that the universe is stranger than we imagined. It's not uniformly filled with matter. It's a web of light and darkness, of structure and emptiness, of of concentration and void. And understanding that Webb, mapping its filaments and bubbles, is one of the great achievements of human science. So the next time you look up at the night sky, remember, you're not just seeing stars, you're seeing the cosmic web, with Earth nestled in one of its bright filaments, and far away, beyond countless galaxies, lies a darkness so profound that it challenges everything we thought we knew about reality. That darkness is real, it's vast, it's growing, and it's waiting. If you found this journey into cosmic emptiness as fascinating as we did, make sure to check out our other deep dives into the universe's greatest mysteries. Until next time, keep looking up and keep wondering about the spaces between the stars.